Okay guys, so far we've been talking about stock processes that are driven by multiple Brownian motion. So we've seen that the differential of such a stock process is given by dSi of t is equal to alpha I of t Si of t dt plus summation j equals 1 to d sigma I j of t Si of t dwj of t. Okay, so we had d Brownian motions driving these stocks, and basically I goes from 1 to m. So we have m stocks, and each stock is driven by d Brownian motions, okay, or d-dimensional Brownian motion. Okay, we also had a discount process. Discount process was basically given by exponential of minus 0 to t r of u d of u. Okay, and we also have seen that d of dt was then given by minus dt rt dt, right? Now what we want to do is we want to figure out what is the differential of the discounted value of the stock. Okay, discounted value of the, or discounted stock process. So we want to see that the differential of discounted stock process. The discounted stock process is given by S of it, which is our stock process, and multiplied by dt. That would basically give us the discounted stock process. So differential of that basically is going to be given by Si of t times d of dt plus dt times d of Si of t. And the cross term would be 0 because we have a dt here. So when we multiply d of sit times d of dt, that would actually, all the terms would be 0, so we don't have to write those terms. Okay, so we're going to get this. And here we can actually substitute this value. So we'll get dt times dsit minus dt rt sit dt. And here we can take dt outside the brackets, dsit minus rt sit dt. Okay, that's the first result we need to remember, and we're going to come back to it a little later in the lecture. We can solve this further. Instead of dSi of t, we can write down this equation right here. If we do so, then we'll get dt. Instead of d of sit, I'm going to write alpha it sit dt plus summation j equals 1 to d sigma ijt sit dwjt. Okay, and then I have this minus rt sit dt term, right? Now here I see all the three terms basically have sit, so I can take that outside the bracket. So I'll get dt times sit, and inside the bracket then I'm going to be left with, what I'm going to do now is I'm going to combine the dt terms together. So I'll get alpha it minus rt dt, because sit I've already taken out. And here I'm going to be left with j equals 1 to d sigma ijt dwjt, right? So let's remember this as equation 2. So we expressed the discounted stock process using the first equation here, or it can be equivalently expressed as the second equation. Okay, now what I want to do is I want to figure out if there exists a risk neutral measure. Okay, so what do we mean really by a risk neutral measure? What are the two things that needs to satisfy? First thing is, for a risk neutral measure, which we're going to denote by p tilde, if this p tilde is a risk neutral measure, then the two measures that we have, the actual probability measure, which is given by p, and the risk neutral measure p tilde, they have to be equivalent. Okay, and what do we mean by equivalent? So if you remember, we basically had a probability space given by capital omega, sigma algebra, and a probability measure P, which basically was the same measure, actual probability measure. So two measures are said to be equivalent if for all sets that belong to our sigma algebra, okay, if probability of a set A is equal to 1 under the actual probability measure, then probability of the same set will be 1 under the risk neutral measure as well. Okay? Or conversely, if probability of a set is equal to 0, okay, then probability under the risk neutral measure of that set is also going to be equal to 0. Okay? So both these measures, they need to agree what events are impossible, okay, which basically means probabilities of impossible events basically are 0. Okay, they need to agree on which events are impossible, and if they agree on which events are impossible, they also agree on which events are 100% possible. Okay, because this is nothing but just the opposite of this, 1 minus that, right? So they basically, if for two probability measures to be equivalent, they have to agree on which sets are impossible, okay, and conversely, which sets have a probability equal to 1. Okay, that basically is what we mean by equivalent. Secondly, if P tilde is a risk neutral measure, if P tilde is risk neutral measure, then the discounted value of the stock process given by SI of t dt needs to be a martingale under P tilde. Okay? So for P tilde to be a risk neutral measure, it needs to be equivalent to our actual probability measure, and under this probability measure P tilde, the discounted stock process basically needs to be a martingale. So if you look at the discounted stock process under the actual probability measure, it's not really a martingale because we have a dt term here. Okay? And when we talked about martingale, you remember we basically said if there is a differential which has a dt term, then that basically process is not really a martingale. Okay, it basically has a drift. But here, so this basically is not a martingale under the actual probability measure, but under P tilde, which is if it's a risk neutral measure, then this discounted stock process needs to be a martingale. Okay, so let's see how we can make this discounted stock process martingale, and thereby we're going to come up with the risk neutral measure. Okay guys, so we already know how we change measure from P to P tilde, right? We basically use Girsonov's theorem to change the measure from P to P tilde. Okay, and if you remember Girsonov's theorem, that time we basically said we define a process given by W tilde of t, which is equal to W of t plus integral 0 to t theta of u d of u, right? In differential terms, we can write this as d of W tilde of t is equal to d of Wt plus theta t dt. Okay, and then we basically define the Radon-Nikodym derivative. Then we basically define a new probability measure, and under that probability measure, this process becomes a Brownian motion. Okay, that's what the Girsonov's theorem basically says. Now, if we look at equation 2, basically right now it's not really in this form. Okay, so what we want to do first is we want to express this equation in this form. Okay, and the way we're going to do it is I want to write this equation as dt sit, okay, summation j equals 1 to d of sigma ij t, and here I want to introduce theta jt dt plus dwjt. Okay, now this is eventually how I want to express this equation 2. Right now it's not really in that form, okay? But I want to express this equation 2 in this form. And why do I want to do that? Because then we actually get this inside the bracket, we get this theta j of t dt plus dw j of t, which basically then becomes in this form. And if I can express this equation in this form, then inside the bracket I can basically substitute dw j of t and then change the measure using Girsonov's theorem. And under that Girsonov's theorem, this then becomes a Brownian motion. Okay, that's the approach I want to take. So I want to express equation 2 like this. And so let's see what we need to, what manipulation we need to do to express equation 2 as this. So if we compare, let's call this equation 3. If we compare equation 2 and 3, okay, let's look at what's multiplying dw term. We have a dwjt, we have a dwjt term here. Multiplying that, we have a summation j equals 1 to d sigma ijt. Here also, outside the brackets, we basically have summation j equals 1 to d sigma ij of t. So we have this term multiplying dwj term. And we also had a dt sit. Here also we have a dt sit term. So our dwj term basically is exactly the same in equation 3 and equation 2. Okay? Now let's focus on what we have in the dt term. Dt term, basically here we have dt sit multiplying alpha it minus rt. Here the dt term basically has dt sit, which we also have here, and then we have the summation multiplying this, right? So what we need to do is, in order to make equation 2 equals to equation 3, we need to equate the dt term. We want to make sure that the dt terms basically agree. So we basically, here the dt term basically has dt sit. Then what else is in the dt term? We basically have alpha it minus rt. That basically is what we have on the dt side. Okay, this basically is multiplying dt. And in this equation, what's multiplying dt? We basically have dt sit summation j equals 1 to d sigma ijt and theta jt. If we make these two equal, then we've been successful in transforming equation 2 to equation 3 in this form, right? As we said, dw term basically has the same terms multiplying it, so we don't have to worry about that. We need to make sure that the things that are multiplying both the equation on the dt side, they are the same. And if they are the same, then we can basically convert equation 2 to equation 3. And in order to make equation 2 equal to equation 3, we need to solve for this. The dt we have here, dt we have here, so it cancels out, this cancels out. So in order to convert equation 2 to this form, we need to make sure that this basically holds true. That basically means j, summation j equals to 1 to d sigma ij t theta jt is equal to I t d. Now this theta basically is called the market price of risk. Okay, and these equations basically are called market price of risk equations Okay, so what we've done is we wanted to express equation 2 in this form. Okay, and why we wanted to express in this form? Because then we can actually substitute for this, we can substitute dw tilde of t, and then we can apply Girsonov's theorem to change the measure. And then we basically get, under Girsonov, we will get this as a Brownian motion, right? So in order to convert equation 2 in the same form as equation 3, we basically needed to make sure that the dt terms basically agree. So we equated what was there in dt terms in both the equations, and we got this. And and if this is equal, then we can rewrite equation 3 as dt si of t, right? We had this, and now summation j equals 1 to d sigma ij t dt. Now instead of writing this, now I'm going to write dw tilde jt, right? And now, as I said, using the multi-dimensional Girsanov's theorem, we're basically going to change the measure, which we just talked about in the previous lecture, multi-dimensional Girsanov's theorem. And under that change of measure, this basically becomes a d-dimensional Brownian motion. Okay? And if this basically is a Brownian motion, then we basically have the discounted stock process, okay, would be sum of various Ito's integral, and since its Ito's integral are basically martingales, using this we basically have shown that under P tilde this basically is a martingale, right? So under P tilde d of sit dt is a martingale. Okay, so the only thing actually that's left to figure out is we need to find out this market price of risk process. Okay, so if you look at this, we basically we have, you know, d unknown processes. Okay, this is theta j, and j goes from 1 to d. So we have d unknown processes, and we have m equations. Because I basically ranges from 1 to m, we basically have m equations and d unknowns. So if we can basically solve for market price of risk process, okay, if we can find out what this theta j is, okay, then we can basically figure out then we can basically define dw tilde of t as this, and then we can change the measure using Girsanov's theorem. So the critical thing to find a risk neutral measure is basically find a solution for market price of risk process. So we need to find this theta j of t. If we can find theta j of t, and if it's unique, then we basically say we have a risk neutral probability measure. So now there are three cases that we can have, right? When we're trying to we have m equations with d unknowns. So we can have three outcomes. One is basically we don't find a solution, okay, for market price of risk equation. So we cannot solve for theta j. If we cannot solve, then basically we don't really have a risk neutral measure. Okay, that's the first thing. Secondly, if we can find more than one solution, okay, if the solution is not really unique, then basically we have more than one risk neutral measure, and you know, pretty much we cannot actually use that model for hedging, because we'll get two different prices of a derivative security, because we have, or n number of prices for a derivative security, as and n basically being the number of measures that we can find. Okay, so if there is no one unique measure, there are multiple measures, then we'll get multiple values of derivative securities. So we cannot really perfectly hedge that security using that model. Okay, and the third case is when we basically find a unique solution for market price or risk process. If we find a unique solution, then a unique risk neutral probability measure exists, and under that probability measure, the discounted stock process is basically a martingale. Okay, guys, so now let's construct an example where we have two stocks which are driven by a single Brownian motion. Okay, so we have two stocks, that basically means I goes from 1 to 2 and j basically is equal to 1. And our market price of risk equation, which is given by this formula, j equals 1 to d sigma ij of t, theta jt is equal to alpha it minus rt. Okay, and let's further assume that all these processes basically are constant. Okay, so we can write the differential for these two stock processes. We can write them as ds1 of t would be alpha 1, okay, and it's constant, s1 of t dt, plus we have a single Brownian motion driving it, so we're going to have sigma 1, which is also constant, s1 of t dw of t. Okay, and likewise we can write down the differential for the second stock. That's going to be alpha 2 s2 of t dt plus sigma 2 s2 t dw t. So we have the same Brownian motion basically driving both these stocks. That's why j is equal to 1. Okay, this is the differential for these two stocks. Now we can rewrite these market price of risk equations right here. So this basically would give us two equations because j goes from 1 to 2, and the equations are going to be alpha 1 minus, I said interest rate is also constant, let's say it's equal to r, should be equal to sigma 1 of theta. That's the first equation, or theta is equal to alpha 1 minus r by sigma 1. Okay, that we get using the first equation from here. Now the second equation is going to be likewise alpha 2 minus r is equal to sigma 2 theta, or theta is equal to alpha 2 minus r by sigma 2. Right? That's what we get from these two market price of risk equations. Now in order for the risk neutral measure to be unique, we basically need these two thetas to be equal, right? So we basically need to have alpha 2 minus r by sigma 2. If this basically is the case, then we have a unique theta, okay? Then we get a unique probability measure, okay? And if we get a unique probability measure, then there is no arbitrage in the model. Okay, that basically is what we need for no arbitrage. But let's assume that this is not the case, that these two are not equal, and let's define mu equals alpha 1 minus r by sigma 1 minus alpha 2 minus r by sigma 2, and let's assume that this is greater than 0. So it's not equal to 0. The difference in these two is basically greater than 0. And let's see how the arbitrage is going to play out in this model. Okay, guys, so in order to exploit this model, what we're going to do is we're going to actually at any point in time we're going to hold delta 1 amount of stock of S1. So this delta 1 is going to be given by sigma 1 times S1 of t. This is the number of shares that of S1 that we're going to hold at any point in time. And delta 2 of t is equal to, we're going to hold, if we go long this, we're going to go short the other stock, and we're going to hold delta 2 amount of S2. Okay, so this basically is a position in S1, this basically is a position in S2. Okay, and we basically are gonna actually, if we need some money in order to take these two positions, we're going to borrow it from the market, and if after taking this position we have some excess money, we're going to invest that in the money market account. Okay, so we basically want to take this position in S1, this position in S2, and if we have excess money left after doing this transaction, we long one, short the other, then we basically going to invest that excess money in a money market account. If we basically are short of money, then we're going to borrow money from the money market account to take this position. Okay, so we have three positions now, one in S1, one in S2, and the third one is basically a money market position. So now, if you basically look at our portfolio, let's look at the value of the portfolio at any point in time and denote that by XT. Okay, now this portfolio basically would be comprised of our stock position and a money market position, right? So at any point in time in t, at any point t, we basically will have delta 1 of S1, delta 2 of S2, and after investing money in this, we'll basically have xt minus delta 1t times S1 of t minus delta 2 of t S2 of t. This basically would be the money that's going to be left with us, which we're going to invest in a money market account. Okay, so we have these three positions: position 1, position 2, and position 3. This is a money market account. So this was the wealth that we had at time t. Out of that money, we basically bought some S1, we basically shorted S2. Okay, and the remaining money we basically invested in a money market account So our portfolio basically comprises of these three positions. So the differential of our portfolio d of x of t would be given by delta 1 of t and the change in the value of s1 d s1 of t plus delta 2 of t, change in the value of s2 ds2 of t, and finally our position in the money market account and this basically is going to accrue interest at the rate of r times dt. Okay, where interest rate is basically constant that we just talked about. So this would be the change in the value of a portfolio for a small change in time. Okay, and let's basically solve here. Now ds1 of t we basically said is right here. We can write d delta 1 of t, which basically delta 1 of t is given by 1 by sigma 1 s1 of t. Okay, I'm going to write that here. ds1 of t we just said basically was alpha 1 s1 t dt plus sigma 1 s1 of t dw of t, right? Then we have delta 2 of t, which is basically a short position, minus 1 by sigma 2 s2t, and here it's going to be alpha 2 s2 of t dt plus sigma 2 s2 t dw t, right? So that basically takes care of this term and this term. That's what I've written here. Now delta 1 t times s1 of t would just give us 1 by sigma 1. So plus we're going to have this third term plus xt minus delta 1 t times s1 of t would be just 1 by sigma 1, and then delta 2 of t basically is minus 1 by sigma 2 s2. Minus minus becomes plus, s2 cancels out, so we'll get plus 1 by sigma 2 times r dt. Okay, so now let's solve here. S basically all these s's cancel out, so what we are left with, we basically will get alpha 1 by sigma 1 dt plus alpha sigma 1 cancels out, we get dw of t. Okay, then minus we'll get alpha 2 by sigma 2 dt plus dwt, and then we're going to get this term plus x of t minus 1 by sigma 1 plus 1 by sigma 2 r dt, and we can solve this further. Now this, we have a minus sign here, so this cancels out, so we have alpha 1 by sigma 1 plus minus alpha 2 by sigma 2. Now I'm combining all the dt terms. Okay, minus we have 1 by sigma 1 plus 1 by sigma 2, right? Sorry, r by sigma 1, r by sigma 2 dt. Okay, and I have this xt here, xt r of dt. So I've just combined all these, this term, and these two terms, these four terms together. This is what I get here, and I was left with this xt, which I've written here. Now we can actually solve this further. We can basically write this as alpha 1. In the denominator we have sigma 1 here, we have sigma 1 here, so we can combine these two terms. We're gonna get alpha 1 minus r by sigma 1 minus alpha 2 minus r by sigma 2, right? dt plus xt times r dt. Now this basically, we had defined this to be equal to mu. right? We basically said, let's define mu as x1 minus r by sigma 1 by x minus x2 minus r by sigma 2. That's exactly what we have here. So we're going to write this as mu times dt plus r xt times dt. And what was this that we were solving for? We were solving for dx of t. Okay? So that's one result that we get. Now let's look at what is the discounted value of our portfolio process. Okay guys, so now we want to look at the discounted portfolio process, and discounted portfolio process would be given by d of t x of t. Okay, this can be written as dt times d of x of t plus x of t times d of dt. Okay, and here we can write dx of t, we already know what it is. It's basically mu dt plus r x of t dt, right? That basically comes from here, and we basically are left with xt. Now d of dt is basically, if you remember, it's given by minus r, it's constant here, then dt times dt, right? That basically is what we're going to get. Let's open the brackets here. We'll get mu dt times dt plus r dt xt dt minus r dt xt dt. This r dt xt dt and minus r dt xt dt cancels out, so we get d of dt times of t is equal to mu multiplied by dt times dt. Okay guys, so one thing to notice here is basically we started with a portfolio. We took delta 1 position in S1, and then we took delta 2 position in S2, and we basically financed this position by taking a position in the money market account. Okay, so if we needed money to basically take this position, we borrowed money from the money market account, and if long one short the other basically generated some cash, we basically invested that money in the money market account. Okay, so at time 0 then, it basically is a self-financing trade. Okay, that basically means that at time 0, the value of the net portfolio would be equal to 0. Okay, because we basically have two positions, one long, one short, and whatever the excess money is, we basically invested in the money market account. So we didn't really have any cash left, right? Everything was basically invested and everything was self-financing. So this was 0. Now we look at when we take the differential of this discounted value of the portfolio, the right hand side basically is non-random and strictly positive. Okay, because mu we said was actually positive. You remember we said basically mu was defined as this, and we said let's assume that this is positive. This is positive. Dt basically was our discount function, which is positive, so the derivative of this basically is positive. Okay, in other words, what we've been able to do is we've been able to synthesize a money market account which basically pays us interest rate higher than R. Okay, which basically is the interest rate that money market account pays. But here we've been using this, we can see that since the derivative is basically positive and non-random, we've been able to synthesize a portfolio using a long stock and short stock and proceeds in the money market account. That portfolio basically acts as another money market account, and it basically has a return higher than R, higher than the interest rate account. Hence basically we've been able to take advantage of the arbitrage. Okay, by going long one short the other and investing the proceeds in a money market account, we basically have created a synthetic money market account that pays us interest rate higher than R, okay, which was basically our borrowing cost, and hence we can basically do unlimited arbitrage. Okay, so we see that, hence we've shown that if this basically condition doesn't hold true, or if basically this we cannot solve for market price of risk, then an arbitrage exists in our model. Okay, and we can take advantage of that arbitrage by going long one stock, short the other, and basically putting the excess money into money market account, and that way we'll be able to take advantage of the arbitrage. Okay, guys? So let's proceed further. Okay, now let's go back to our example where we had M stocks, and each of these stocks were driven by a d-dimensional Brownian motion. That time we said the differential of the stock is basically given by dsi of t is alpha I of t s I of t dt, and is driven by d Brownian motion going from j equals 1 to d sigma I j of t s I of t dw j of t. Okay, now what we want to do is we basically want to do something very similar to what we've just done. We basically want to take position in each one of these stocks and invest the remaining money in a money market account. So we basically are going to start with some money xt, and we're going to take delta I of t position in si of t. So for I going from 1 to m, okay, we'll have basically delta I position in each one of these stocks. Once we take position in these stocks, whatever money is remaining from our portfolio, we basically are going to invest that money in a money market account. Okay, something very similar to what we've just done. And we want to look at what are the change in the value of the portfolio. The change in the value of the portfolio then is going to be given by change in the value of our stock position, which is given by delta I of t d s I of t. Okay, and this we basically have to sum from I going from 1 to m because we have m number of stocks. So this basically is a change in the value of the position in our stock, and that stock goes from 1 to m. So that basically is the total change because of the position in the stock. And then we basically have our money market account, and how much money did we invest in the money market account? We basically had this much money, and we bought I equals 1 to m. We basically bought delta I of t s I of t. This was the amount of money that actually went in our stock position. Okay, sum over 1 to m. After buying the stock, this much amount of money was left, which we basically invested in a money market account, which accrues interest now at the rate of RT dt. Okay, so this basically is the change in the value of the portfolio from stock position. This is the change in the value from the money market account. Now what we can do is we can combine this term and the summation term. So we'll get xt RT dt. Okay, this xt term multiplied by RT dt I've written here, and now let's write the summation term. I equals 1 to m. Both the terms have delta I of t, so I'm going to take delta I of t outside the bracket, and I'm going to be left with dsi of t here, and after taking delta I of t, I'm going to be left with si of t RT dt. Right? That's what I'm going to get. Now let's compare this to, if you remember when we just started the lecture, the equation number 1. We said d of the discounted value of the stock basically is given by this equation, which is very similar to this. So from equation 1 we can see that we can rewrite this as x of t RT dt plus summation I equals 1 to m delta I of t. Now instead of this, what I'm going to do is I'm going to write this as d of sit dt, discounted value of the stock, divided by, so we basically had everything here. We had this dt here, which now goes in the denominator. Okay, so this is what we're going to get as d of x of t. Now next what I want to do is I want to figure out what is the differential of the discounted value of the portfolio process. Okay, this was the differential of the portfolio process. Now I want to figure out the differential of the discounted value of the portfolio process. So let's do that. Now the discounted value of the portfolio process can be written as d of dt x of t. This is basically nothing but dt times dx of t plus x of t d of dt. Okay, so here we can write d of dt. Dx of t, we just got this particular equation right here, so let's write that. Xt times rt dt plus summation I equals 1 to m delta it times d of s of it dt whole divided by dt. Okay, that basically is the first term, and then we have xt, and d of dt is nothing but minus dt rt dt. Okay, so we can open the brackets now. We'll get dt xt rt dt plus summation I equals 1 to m delta I of t d of s I t dt, and this dt cancels out. Okay, and then I have this minus dt xt rt dt, right? I have dt xt rt dt and minus dt xt rt dt, so this basically cancels out, and I'm left with d of dt xt is equal to summation of I equals 1 to m delta I of t d of s I t dt. Now we just said that under p tilde, this basically the discounted value of our stock process was a martingale. Okay, we just showed you. So if under p tilde discounted value of the stock process is a martingale, the discounted value of the portfolio process is also a martingale, because this is nothing but sum of Ito's integrals, right? And Ito's integral we just said basically a martingale under p tilde. Hence, the discounted value of the portfolio process is also a martingale under p tilde. Okay, so that's another result to actually keep in mind, that the discounted value of the portfolio process is also a martingale under p tilde. Now, how does that basically lead to no arbitrage is what I would like to discuss next. So basically what I want to discuss is, if our discounted value of the portfolio process, okay, is a martingale under p tilde, then there is no arbitrage in the model. And why that's the case, let's discuss that next. Okay guys, so we just saw that under the risk neutral measure p tilde, the discounted value of the portfolio is basically a martingale. And I basically said that if under the risk neutral measure the discounted value of the portfolio is basically a martingale, then there is no arbitrage in the model. Okay, and let's basically see why there is no arbitrage in the model. Okay, first of all, let's basically try to define what is arbitrage, and we already know what is arbitrage, right? So basically arbitrage strategy is that we start with no money. So we basically have a portfolio whose value at time 0 is equal to 0. That basically means that we don't start with any money, and we basically come up with a trading strategy such that no time in the future there is any probability of losing any money. So we never lose any money. That means that probability that x of t is greater than equal to 0 is equal to 1. That basically means that the value of the portfolio never goes negative. We never lose money. That's why probability is equal to 1. And there are at least a few times when we can actually make some money. Okay, so probability that it's strictly greater than 0 is greater than 0. Okay, or there is some probability that we actually make some money. So this is a strategy where we start with no money. there is absolutely no chance of losing any money, and there is at least some chance of making money. Okay, this basically is what arbitrage is. Okay, again, we basically have a strategy where we're starting with no money. We have absolutely zero probability of losing any money. Okay, so probability that we always are greater than 0 is equal to 1. So we're never going in the negative territory. And there are at least a few chances, or there is some probability that we actually going to end up making some money. Okay, so that basically is arbitrage, right? Because we start with 0, we don't have to put any money in the trading strategy. We have absolutely no chance of losing money in the future, and there is some chance of actually making some money. So if somebody gave you a trade to do like that, you would do that trade all day, right? Because there is absolutely no chance of losing anything, and there is some chance of making money, and that basically is the classic definition of arbitrage. Okay, and let's see why, if the discounted value of the portfolio is a martingale, that basically means that there is no arbitrage in the model. Okay guys, so because under the risk neutral measure, the discounted value of the portfolio is basically a martingale, that basically means dt times x of t given information at time s is equal to ds times f of s, right? And this, from here we can basically see that this is also true, that dt xt given no information basically would be equal to x0, and x0 basically in our trading strategy we basically are going to start with 0 money. So initially we basically going to start with 0 money, that's why x0 is equal to 0. And this basically implies that there is no arbitrage. Okay, expected value of a random variable is equal to 0. That basically there is no arbitrage. Why? Because let's see how we can get expected value as 0 of a random variable. So let's assume there is a random variable y, and we say expected value of the random variable under some risk neutral measure is basically equal to 0. How we can get expected value 0? Either y is 0 almost surely. Okay, if y is 0 almost surely all the time, then basically we'll get expected value as 0. Or if there is a probability of y being positive, okay, then there has to be a probability of y being negative as well. Okay, then only when we take the expected value, we have a chance of cancelling it out and basically get the probability expected value equals to 0. If y was never negative, it was always positive, okay, it could take various positive values, never a negative value, then when you take the expected value of the random variable y, it would not be 0, it would be positive, right? Because all the outcomes were positive, and if you take the expected value of a random variable where all the outcomes are always positive, then you would get the expected value also as greater than 0. In order to make it 0, if there is a positive value, you also need a negative value. Okay, and that basically is what's happening here as well. Because the expected value of this is equal to 0, that basically means that dt is basically the discount process. Okay, discount process, as we said, basically is always positive. Okay, so the only way this basically expected value can be 0 is if xt basically takes a positive value, it also needs to take a negative value. Okay, that's the only way we can cancel it out, and basically expected value can become 0. If it's always positive, which basically is the case required for arbitrage, we always want the portfolio to be positive. If portfolio's value is positive always, then the expected value will not be equal to 0. Expected value would be positive. Okay, hence it would not be a martingale. So for martingale, basically we want this expected value under the risk neutral measure or discounted value to be equal to 0, and the only way this can be 0 is if xt has a positive, can take positive values, it also needs to take negative values. And the moment it can take negative values, it goes against this condition of arbitrage, that we can lose money. Arbitrage basically says we can never lose money. But here we are saying if we are taking a positive value, we also need to be taking some negative values. Okay, and that destroys the arbitrage argument right there. that we basically can take a loss sometime in the future, whereas arbitrage condition basically says that we can never take a loss in the future. Okay, so that's why when we say discounted value is a martingale, the portfolio process is a martingale under the risk neutral measure, that basically implies that the portfolio, if it takes a positive value, it also needs to take a negative value. Hence, under risk neutral measure, there is no arbitrage. And since risk neutral measure is basically equivalent to the actual probability measure, if there is no arbitrage in the risk neutral measure, just because these two measures are equivalent, there cannot be any arbitrage in the actual probability measure as well. Okay? So that's why that basically is very important. And this basically is called the first fundamental theorem of asset pricing. Okay? First fundamental theorem of asset pricing basically says that if there is a probability, if there is a risk neutral probability measure in the model, then there is no arbitrage. And the reason why, because if there is a risk neutral measure, then the discounted value of the portfolio becomes a martingale. And if the discounted value of the portfolio is a martingale, then by definition, because of this reasoning, there cannot be any arbitrage in the model. Okay? So that's the first fundamental theorem of asset pricing. Hopefully that discussion was clear. Okay? So let's move forward.